All right, hey everybody. We're going to continue with some of these derivative rules, and we're now going to have a rule that's allow us to kind of look at combined functions. So two rules actually, the product rule and the quotient rule. So first off, the product rule. So this is the product rule. If you have two functions f and g that are both differentiable, the derivative of f times g, f of x times g of x, will be f of x times d over dx gx, so the derivative of g, plus the derivative of f times g of x, which can be more kind of abbreviated as f g prime plus f prime g. This is a nice little abbreviation to remember. So let's look at trying to prove this using the limit definition, see how difficult that is. So the derivative of f of x times g of x by the limit definition is going to be the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x. And what we're going to do is in order to handle this thing, what we're going to do is a little add and subtract. We're going to do f of x plus h times g of x minus f of x plus h times g of x. So sometimes we multiply both the numerator and the denominator by the same thing in order for us to kind of keep things legal, right? But here we can add and subtract the same thing from the numerator in order to keep things legal. Why is this going to be good? Well, what we're going to do is what we're going to see is we can kind of put this into two fractions. Okay, so what we're doing is we're collecting two of the terms in the first fraction. So we're going to be splitting this limit into the sum of two limits. So we have the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x plus h times g of x. And then the second one, we have f of x plus h times g of x minus f of x times g of x. So we just took, in the first one, we just took this and we took that. Those went into the first fraction, and the second one is going to take these two terms, but I just swapped the order. What I'm going to do now is I'm going to write this as a product of two limits. The limit as h goes to 0 of f of x plus h, because that's a common factor of both of these, and then the limit as h goes to 0 of g of x plus h minus g of x. And then I'm going to, on the other one, I'm going to take out g of x can actually be factored out. There's no h's involved, so it's actually, I don't have to write it as a limit. G of x, limit as h goes to 0 of f of x plus h minus f of x over h. Nice thing here is the limit of f of x plus h as h goes to 0 is simply f of x. This here is just the definition g prime of x. That's what that is. Then we have g of x, and then this here is the definition of f prime of x. And that's our proof. That's how we get the product rule. It's not too bad. So let's take a look at this, the derivative of this y equals x squared sine of x. So in this case, I'm going to consider f of x to be x squared and g of x to be the sine of x. Okay, so f prime of x, as we know from the power rule, is going to be 2x. And g prime of x is the cosine of x. Okay, so y prime is f g prime plus f prime g, which I'm going to put those parts in. We have x squared times the cosine of x plus 2x times the sine of x. And that's it. Now, in this example, I'm actually naming this function f of t, so I'm not going to use f's and g's as I do the derivative, but what I'm going to do is just put little prime markers on the different parts that I'm going to do. So the pattern is when I have the product of square root t and a plus bt, so it's going to be square root t prime times a plus bt plus square root of t times a plus bt prime. That's a fine way to remember this. Now, the square root of t is just t to the 1/2. And so the square root of t prime, the derivative of that, is going to be 1/2. You bring down the power as a coefficient, then t, and we subtract 1, negative 1/2. So that's going to be 1/2 t to the negative 1/2 times a plus bt plus square root of t times, what's the derivative of a plus bt? It's b, because this is, the derivative of a is 0, and the derivative of bt is just b. Now we're going to clean this up a little bit. This is 1 over 2 root t. T to the negative 1/2 would be a square root of t in the denominator. And then I'm actually going to have times a plus bt. I'm going to be going to move things around a little bit. Now, at this point, I've actually got the derivative. I'm just doing a little bit of tidying up for my own for my own pleasure. So we've got, let's see, the first term, I'm going to a over 2 root t plus, so b t over 2 root t plus b root t. Nice. The thing about this middle term is b t over 2 root t. 2 divided by the square root of 2 is just b times square root of t over 2. So in fact, this can be written as a over 2 root t plus, so b root t over 2 plus b root t is going to be 3b root t over 2. This is my answer. Although I could have stopped right here if I wanted to, but still, that's fine. So suppose I have h of x is x times g of x. I don't know what g of x is exactly, but I know g of 3 is 5, and I know that g prime of 3, the derivative at 3, is 2. So if I wanted to find the derivative of h at 3, this is going to be, it's going to be x prime times g of x, let me put this another way. Let's just write out what would be h prime of x, just generally, right? It's going to be x times g prime of x plus x prime, like the derivative of x, which we know is 1, times g of x. Let's clean this up a little bit. X g prime of x plus 1 times g of x. Now, if h prime of 3 then is going to be, if I'm plugging 3 in for x, it's going to be 3 times g prime of 3 plus g of 3. I'm actually given those. 3 times g prime of 3 is 2 plus g of 3 is 5. That's 6 plus 5 is 11. So a bit of a little puzzle riddle thing, but all of the pieces are there. You can solve that thing. Okay, so taking the derivative of a product is no problem. Now we'll take a look at the this thing called the quotient rule. Okay, so if f and g are differentiable functions, then the derivative of f of x over g of x follows this pattern. It's f prime of x, g of x, minus f of x times g prime of x over g of x squared, which abbreviated f prime g minus f g prime all over g squared. This would be like a very quick way of writing this thing. So let's take a look at the proof of this and see how we can do this. So here's the definition by the limit. The derivative of f of x over g of x is the limit as h goes to 0 of f of x plus h over g of x plus h minus f of x over g of x, all divided by h. All right, so what we're going to do to start, we're going to just get common denominators up top, which means I'm actually going to move things over just a tad in order to put, for the first term, I'm going to multiply it by g of x over g of x. And the other one's going to be multiplied by g of x plus h or g of x plus h. So now we can actually write g of x plus h times g of x all in the denominator with the h. So we have limit as h goes to 0 of g of x plus h times g of x times h, and we have f of x plus h times g of x minus f of x times g of x plus h. We're kind of almost there. What we're going to do now is we're going to add and subtract the term f of x, g of x, f of x, g of x in order to group these things together, similar to what we did in the product rule. So the first limit that we're going to take is f of x plus h, g of x, minus f of x, g of x, and then divided by g of x plus h, g of x, and then an h. The second one, I'm actually going to put as a minus here, minus the limit as h goes to 0. So that was this first term, and this last term got used. I'm going to keep the minus, and so it's going to be minus f of x, g of x plus h, minus f of x, g of x. And this is all over g of x plus h, g of x, and then the h. Okay, so you can already see that the limits are kind of are showing you the derivatives of a couple of these. So I'm actually going to factor out the stuff that can all go to where the h's can go to 0. So for this first one, limit as h goes to 0, the stuff I can pull out is I'm going to pull out of g of x over g of x plus h over g of x, or times g of x. And what I'm left with is this other limit as h goes to 0 of f of x plus h minus f of x. For this other one, I'm going to pull out the g's, the limit as g of x plus, this is the limit, another limit as h is going to 0 of, we have, actually here I'm going to pull out f of x, and I'm going to pull out g of x plus h times g of x. And what I'm going to keep in this limit as h goes to 0 is the g of x plus h minus g of x. Okay, now this limit here, there's no problem with just plugging in 0 for h. So I get g of x over g of x squared. I know it's a little silly to have g of x over g of x, but the point is that this is going to all go back together in the fraction at the end. This here is f prime of x. Okay, now this here is going to be f of x over g of x squared, and this last limit is just it's g prime of x. And so I do get, indeed, g of x squared on the denominator, and I can write f prime of x, g of x, minus f of x, g prime of x. That's the product. That's the quotient rule. So not bad, right? Fit on one page. Okay, let's take a look at this and let's find its derivative. Now I'm going to just call this numerator f of x, the denominator g of x. And so if I'm going to follow the pattern, y prime is going to be f prime of x, g of x, minus f of x, g prime of x, all over g of x squared. So what is f prime of x? The derivative of this polynomial in the numerator, using the product and the sum rules, right? 2x plus 1 g prime of x is going to be 3x squared. So putting everything in, so the first f prime is 2x plus 1, g of x, as we have already, x to the third plus 6. Then we have minus f of x, which is x squared plus x minus 2 times g prime of x, 3x squared. Okay, all of that is divided by x to the third plus 6 squared. I'm not going to do anything else with that. It is perfectly fine the way it is. No need to expand it, simplify it, all of that. This is looking fine to me. All right, now let's look at this curve, y equals square root of x over 1 plus x squared, and let's find the tangent line at the point 1 comma 0.5. So y prime is, as I said, it's f prime g minus f g prime over g squared. So let's evaluate that. The derivative, remember, if f of x is square root of x, that's x to the 1/2. F prime of x, we've done this a few times, f prime of x, it's 1 over 2 root x. It's helpful to remember that for the square root, because we are going to see it again and again. So the derivative of square root of x, 1 over 2 root x. So we have 1 over 2 root x times 1 plus x squared, that's g of x, right? Minus square root x times the derivative of 1 plus x squared, which is going to be 2x, right? Just to remind you, g of x, that's my 1 plus x squared. So g prime of x is, the derivative of 1 is 0. The derivative of x squared is 2x, right? All of this over 1 plus x squared. Let's evaluate this when x equals 1. This is, I'll write it as like y prime evaluated when x equals 1. So we have 1 over 2 root 1 times 1 plus 1 squared minus square root 1 times 2 times 1 all over 1 plus 1 squared. Oop, I didn't put the squared before. That's squared. A lot of ones. Let's see what this comes out to be. We have 1 over 2 times 2 minus 1 times 2 all over 2 squared. So we have the first term, there's 1 minus 2 over 4. That's negative 1/4. Yeah, negative 1/4. That's the slope. And remember the equation, it's y. You can write it like y equals 0.5 plus, I guess it would be minus 1/4 times x minus 1. So this is my y, the point y0. This is the point x0, and this is the slope. This is y prime. My point is 1 comma 0.5, so that's where you put that stuff in. This is fine. I mean, I could clean this up a little bit if I wanted to, but I don't really want to. 0.5 is negative 1/4. Let's see, 0.5 minus a minus, that'd be plus a fourth. That'd be x plus 0.75, or plus, let's write it as 3/4. That's fine. No need to get too fancy. Here's a theorem that we can now prove. The derivative of the tangent is the secant squared. And I'm going to actually prove this using the quotient rule, because the d over dx, the derivative of the tangent of x, this is my little proof, that's the derivative of the sine of x over the cosine of x, right? So this is going to be, by the quotient rule, right? It's going to be the sine of x, the derivative of sine of x times the cosine of x minus the sine of x times the cosine of x derivative all over cosine squared of x. Now, what's the derivative of the sine of x? That's the cosine of x. Cosine of x, cosine of x. What's the derivative of cosine? We already have that. Remember, it's negative sine of x. Cosine times cosine is cosine squared x minus sine x times minus sine x. Well, that's going to be plus sine squared x over cosine squared x. And remember what sine squared plus cosine squared is? It's 1. That's the Pythagorean identity. 1 over cosine squared x. Now 1 over cosine is the secant of x. That's just the definition of a secant. So 1 over cosine squared is it's the secant squared of x. Okay, so the derivative of the tangent is the secant squared. Furthermore, we have these 3 derivatives that we can actually prove. I'm not going to prove them here, but they can be proved basically just using the quotient rule. The derivative of the cosecant is negative cosecant x times cotangent x. The derivative of secant of x is the secant of x times the tangent of x, and the derivative of cotangent x is negative cosecant squared. Remember that the secant of x is just 1 over cosine x, the cosecant of x is just 1 over sine of x, and the cotangent of x is just cosine x over sine x. All right, let's take a look at this derivative. We want to take the derivative of secant x over 1 plus tangent of x. So actually, what I kind of would like to do is write this as 1 over cosine x times 1 over 1 plus sine x cosine x. The reason I'm going to do this is if I actually distribute that cosine x into the denominator, it becomes 1 over cosine x plus sine x. And I actually like that a little bit better. But I want to show you kind of doing it in both ways. We can, if we use the quotient rule here on the right hand side, we'd say f of x is just 1, and g of x, or actually I shouldn't use f. I'll just write the derivative out using like this way. So f prime of x, it's going to be the derivative of the numerator 1 prime times cosine x plus sine x minus 1 times cos x plus sine x prime all over cos x plus sine x squared. Nice thing is this first term, the derivative of 1 is 0, so that first term is gone. And we have minus, the derivative of cosine is a minus sine of x. The derivative of the sine of x is the cosine of x. And down below, we've got cosine x plus sine x squared. That means we get, well, I'll write it in this order. So we have cosine squared x plus 2 sine x cos x plus sine squared x. The sine squared plus the cosine squared gives you a 1 in the denominator. So I'm going to have 1 plus 2 sine x cos x. And up top it's going to be sine of x minus cosine of x. So that's the derivative. But I can write this in a different way. I can do this in a different way if I just take the beginning function f prime of x. It's going to be secant x derivative times 1 plus 10x minus secant x times 1 plus 10x prime. all of this over 1 plus tan x squared. So following the rules that I had in the previous, I have the derivative of a secant is secant x tan x, all of that times 1 plus tan x. And then I'm going to subtract secant x and secant x times the derivative of 1 plus tangent of x. The derivative of 1 is 0, and the derivative of tangent is secant squared x. All of this over 1 plus tangent x. So I'm going to write this as 1 plus 2 tan x plus tangent squared x. Now you might not remember your all of your Pythagorean identities, but 1 plus the tangent squared of x is equal to the secant squared of x. Do you remember that one? If you multiply through by the sine squared of x, you multiply through by the cosine squared of x, what you get is cosine squared plus sine squared equals 1. So down here, the 1 and the tangent squared, I can write secant squared x if I wanted to. But I mean, this is all, it's all kind of a bit messy. But so we have secant x tan x plus secant x tan squared x minus secant to the third x. All this over secant squared x plus 2 tan x. Now, if I wanted to, I could probably fiddle around with things, and I could show that these two things are indeed equal. I don't really feel like doing that, but it is. You can kind of see what would get you there. I think if I was to, yeah, I guess I'm going to do one little thing. I'm going to factor out the secant of x out from the numerator, so I get the tangent of x plus tangent squared x minus secant squared x, and that's over this secant squared x plus 2 tangent x, and just observe that this Pythagorean identity that relates the tangent and the secant, you can, if you have tangent squared minus secant squared, this here, that's -1. So we can simplify a little bit, but I don't know. I don't really want to do that. Okay, that's all I'm going to say. Get some practice. Use the quotient rule. Bye.